This video is probability, the multiplication rule, and conditional probabilities. If we flip a coin twice in succession, what would the sample space be? So the sample space are all the possible combinations that could happen. So I have them listed here. You could flip the coin and the first be heads and the second be heads, or you could flip the two coins and the first would be heads and the second tails, or you could flip the two coins and the first be tails and the second heads, or you could flip the two coins and the first would be tails and the second would be tails. You could make a tree diagram to show this. The first could be heads and the second could be tails. And if the first was heads, the second could be heads or tails. If the first was tails, the second could be heads or tails. And you can get these same things listed: heads and heads, heads and tails, tails and heads, tails and tails. Either way, you get 4 outcomes. So what is the probability that the first flip results in heads? So you can look here. The first flip is heads here and here. So that's 2 out of 4, which is 1/2 or 0.5. What is the probability that the second flip is tails? Okay, the second flip being tails, let's see, second flip's tails here and here. So that would also be 2 out of 4 or 1/2 or 0.5. What would the probability that the first flip results in a head and the second flip results in a tail? So the first flip is heads and the second is tails. There's only one right there. So that's just 1 out of 4 or 0.25. So what we want to notice here, though, is that the probability of both happening together, 1/4 or 0.25, is the same as the probability of one times the probability of the other. So if you think about, if we want to know what's the probability of flipping a heads first and a tails second, we can find the probability that the first one is heads, which we said was 1/2. And it won't let me write 2 for some reason. Times the probability that the second one is tails. The probability that the second one was tails was 1/2. If we multiply that out, we get 1/4. So let's talk about drawing cards without replacement and thinking about this the same way. Suppose we draw one card and then, without replacing it back and reshuffling the deck, we draw a second card. So we didn't put the card back in after we drew the first card. What is the probability that we draw 2 aces? So first, what's the probability that the first one is an ace? Well, the probability that the first one is an ace, let me erase that and try again. There are 4 aces out of 52 in the deck. You can reduce that. That would be, I believe, 1 out of 13. What is the probability that the second card is an ace? Well, here's the thing. Let's pretend that the first card was an ace. So now, is there 4 aces anymore left in the deck? There's not, because we didn't replace it. So now there's only 3 aces in the deck. Now, does the deck still have 52 cards in it? No, because we took out an ace. That means there's only 51 cards. So the probability of drawing an ace both times, we multiplied the first time being 450 over 52 and the second 3 out of 51. So we would get 0.0045, and this is called conditional probability, because the second probability for the second ace is on the condition that the first probability that the first card drawn was an ace. So that's what's called conditional. Independence. Two events are independent if the outcome of one has no effect on the probability of the other. Think back to the card scenario. When we drew that first card and didn't replace it, it had an effect on the probability that the second one would have be an ace. For the first card, the probability that it was an ace was 4 out of 52, but once we took the ace out, now the probability changes and it's only 3 out of 51. Note that saying that two events are independent is different than saying that the two events are mutually exclusive. So please know that they're not the same thing. Remember, mutually exclusive are events that can't happen at the same time. If two events are independent, they have no effect on each other's likelihood of occurring. If two events are mutually exclusive, they cannot occur together, so they do not have an effect on each other's likelihood of occurring. So independent is just they don't affect the probability of the other. But if they're mutually exclusive, they can't happen at the same time. All right. Example 1. Determine whether these events are independent. A fair coin is tossed 2 times. The two events are A is the first toss. The first toss is heads, and B, the second toss, is heads. Well, the probability of the first event happening is going to be 1/2. And the probability that the second one is going to be heads is also 1/2 because the first toss is not going to affect what happens on the second toss. So that is definitely independent. The two events, A is that it will rain in Maryland, Frederick, Maryland, and B is that it will rain in Thurmont. So you might think whether it rains in Frederick has no effect on whether it'll rain in Thurmont or not, but actually if it rains, it's more likely that it's going to rain in Thurmont on days that it will rain in Frederick because we're so close. So those would not be independent events. You draw a red card from a deck, then draw a second card without replacing the first. That's like the probability of the aces we found earlier. If we do not replace that first card before we draw the second, that will have an effect on the probability of the second card. So because we no longer have a 52 card deck, we now have a 51 card deck. So this would not be independent either. Not independent. Okay, you draw a face card from a deck, then replace it and reshuffle the deck before drawing the second card. That would definitely be independent because you replaced it first. So it doesn't change the probability. So now a face card, there are 12 face cards out of 52. If we replace a face card, we still have 12 out of 52 face cards. So it doesn't affect the probability of the second. Alright, so using what we've learned, we can form the multiplication law rule for independent events. So if A and B are independent, then the probability of A and B occurring is just the probability of A times the probability of B. It's just multiplication. If you have more events, you keep multiplying. So if you wanted to know the probability of A and B and C, then you would multiply the probability of A times the probability of B times the probability of C. So if you had the probability of A and B and C and D, it'd be the probability of A times the probability of B times the probability of C times the probability of D, and so on and so forth. Alright, let's look at this example. Suppose you flip a coin and roll a 6-sided die once. What is the probability that you'll get tails and an even number? Tails and even. So you're going to find the probability of getting a tails, find the probability of getting an even number, and multiply them together. So tails, there's 1. There's 1 out of 2. And even, there are 3 even numbers out of 6, which is the same as 1 out of 2. This would be 3 out of 12, which is 1/4. If I had reduced this 3 over 6 to 1 over 2, 1/2 times 1/2 is 1/4. So either way you get 1/4. Your answer is 0.25. Assume you have a 52 card deck and you select 2 cards at random. Also assume that you replace and reshuffle after each section. Find the probability of drawing a king first and then a black card. Why don't you pause the video and then unpause to find out the answer. Okay, we're finding the probability of a king and then a black card after, that's with replacement. So find the probability that the first one is a king, find the probability that the second one is a black card, and we multiply the 2 probabilities together. So there are 4 kings out of 52. You can reduce that if you want to 1 over 13. There are 26 black cards out of 52. I would just multiply these out the way they are. 4 out of 52 times 26 out of 52. And we get 0.0385. Alright, example 4, left-handed population. About 9% of people are left-handed. Suppose that 2 people are selected at random from the U.S. population. Because the sample size of 2 is very small relative to the population, it's reasonable to assume that these 2 people are independent. What is the probability that both are left-handed? So, what's the probability that both are lefties? So that's the probability of the first one being a left-handed person and the second one being a left-handed person. So you're going to find the probability that the first one's left-handed and multiply that times the second one being left-handed. And again, they told us in the problem that this was independent. So that means one event occurring is not going to affect the probability of the other event occurring. So the probability of the first one being left-handed, well, if there are 9% of people are left-handed, then the probability is 0.09. And because it's independent, the second one's going to be the same thing, 0.09. That's what 9% is. So 0.09 times 0.09 is 0.0081. 0.0081. Alright, assuming the probability of having a boy is 0.5, find the probability of a family having 3 boys. So why don't you pause the video and try this one. Okay, for this one, for probability of 3 boys, you find the probability that the first one's a boy, the probability that the second one's a boy, and the third one's a boy. Each pregnancy is independent of the other, so the probability for each is 0.5 because of what we set up here. So 0.5 times 0.5 times 0.5 is 0.125. So the probability of a family having 3 boys is 0.125. Alright, so we're going to stop the video here and we're going to pick up the multiplication rule for dependent events because all the ones that we've done since I introduced the rule for multiplication have been independent events. So let's do dependent events in the next video.